Hello, fellow students. Today, we are going to talk about complex numbers. So first, we are going to talk about how to represent a complex number. We usually denote a complex number by the letter Z. This letter here. It is just a convention. We will write it in the form a plus bi, where a and b are real numbers, and the I is the famous square root of -1. It is called the imaginary unit. The real part, defined by this Re over Z, is defined to be this A. So this thing. And the imaginary part of the number is B. It's basically this thing. You need to be careful here. The imaginary part is defined without the I. So it's just this B. You can't write the I. Next, the modulus of Z is the square root of A squared plus B squared. And this basically comes from the Pythagoras theorem. And the other thing, the arc argument of Z is actually an angle, but mathematicians call it argument. It is defined by the arctangent of B over A. So you basically divide the imaginary part by the real part, and then you take the inverse tangent. Next, geometrically, a complex number can be represented on the complex plane as this. It is not a vector though, as it always stems from the origin, and you don't write an arrow here. The modulus is the length of the complex number in a complex plane, and the argument is the angle the complex number makes with the real axis. And the argument is defined between -pi to pi. So in this case, the modulus of Z is square root of 1 plus 1, which is square root of 2. So it's this part squared, and this imaginary part, this 1 behind the I you can't see it, but it's 1i. And the argument of the complex number, you take it to be the arctangent of 1 over 1, which is pi over 4. Depending on the quadrant Z is in, you may need to plus or minus 1 pi, as the inverse tangent function only gives you angles in the first and the fourth quadrants. And the arctangent runs from -pi over 2 to positive pi over 2. So if you have a complex number in the third quadrant, in this case, like -1 minus I, and you need to minus pi to shift the first quadrant result given by the arctangent function to the third quadrant. So if you just calculate B or A, because B and A is both negative, their quotient will be a positive number, and the arctangent will give you this angle. It's a positive angle, and you need to minus 1 pi to get to there. Similarly, if you got the complex number in the second quadrant, like this one here, -1 plus I, the B or A will be negative, but the arctangent will give you the result in the fourth quadrant. This is because it does not know whether it is B or A that is negative. So if you putting a negative number in the arctangent function, you automatically give you a result in the fourth quadrant. In this case, you need to plus a pi. So you basically rotate anti-clockwise, and you can get this number. And we now have another point to go through, which is the polar form. Instead of writing Z equals A plus BI, we can represent a complex number in a different, totally equivalent, and a more geometrical form. We've written this as Z equals to the Greek letter rho times the sum of cosine of theta plus sine of theta. And this equivalently we write as rho cis theta. This cis function is shorthand way to write this cos plus I sine. And this rho is the modulus of Z, and theta is the argument of Z. I've given them new names also to save time of writing, because it's not a lot quicker to write a single theta here instead of writing ARGZ. So this method is based on the decomposition of the real and imaginary parts into their respective axes. So you know, as the axes are perpendicular, you have a right angle triangle here. It's evident that the cosine of theta is A over rho, and the sine of theta is B over rho. As you know, basic tricks. So cos is adjacent over hypotenuse, and the sine is opposite over hypotenuse. And the rearranging gives you this. A is equal to rho cos theta, B is equal to rho sine theta. So if we now substitute A and B into Z, you get this. If we factor out the row like this, in front of these two here, we get this thing. And just using our definition, cos plus I sine is defined as cis. Now you know that you can also use a complex number's length and angle to specify it. But an important point to remember would be the fact that there are more than one possible value of theta. So using our previous example, z equals to 1 plus I in the polar form, you can see that the modulus of z will be square root of 2, as we calculated in the previous slide. And the argument of z will be pi over 4. Therefore, we can say that z is equal to the square root of 2 times the sum of cosine of pi over 4 plus I sine of pi over 4. Or you can just write it as 6 pi over 4 if you want to quicker. However, because the period of sine and cosine is 2 pi, if you have a sine of a number plus 2 pi, this thing will just equal to sine of x, just number itself. The 2 pi just basically doesn't do anything there. So if you take your theta, which is a pi over 4, and you plus 2 pi to it, you get 9 pi over 4. This will also be a possible choice of argument. Due to this reason, to avoid confusion, we'll restrict the domain of theta from minus pi to pi. This is called the principal branch of the argument. So if you write z equals to square root of 2 times 6 of pi over 4, this is the accepted representation. If you can see there, this is the smallest angle you can measure. If you measure the argument like this, with one extra cycle, you go around about 360 degrees more, which is another 2 pi, and you got 9 pi over 4. This is not accepted. And if you write your argument like this, you measure it clockwise, this, you get negative 7 pi over 4. This is also not accepted. The only time you can go clockwise to measure a negative angle is if the complex number lies in the third or the fourth quadrant. In the first quadrant, you measure it anti-clockwise. And this will be important when we are doing roots of complex numbers. You need to remember to check that your argument is between the negative pi and the pi domain. Another form you need to know is Euler's form. A complex number can also be written in Euler's form based on Euler's formula. So it says that e to the power of I theta is equals to cosine of theta plus I sine of theta. It's a pretty magical formula. It may seem strange, but it's true. It's one of the most important formulae in maths. So if you just substitute this left-hand side in there, you can see we previously have polar form there, and you use this formula. This thing is equal to this thing. So you have z is equal to rho times e to the power of I theta. It's a very elegant and a short way to write a complex number. Important thing to note is that the complex exponential, this thing here, this e to the power of I theta, will always have a modulus of 1. Because if you take the modulus of this and you use Euler's formula, like substitute this thing here, and the same as taking the modulus of cosine of theta plus I sine of theta, and use the definition of modulus, you square the real parts plus the square of the imaginary parts, and you have this. Now if you remember your Pythagorean identity, you know that cos squared plus sine squared is always 1, and the square root of 1 is just 1. It is not negative 1, be careful. And this will represent a unit circle in the complex plane. So this picture shows the position of e to the I theta for all theta. Immediately following the important property, we'll do an example. This is from chapter 4b, question 3 in the book. The question is, on a complex plane, sketch the region corresponding to the modulus of z equals 2. Firstly, we'll use Euler's form. We can write z as a rho times e to the power of I theta. Its magnitude is equal to 2. We now can separate this product. You know, the modulus of a product is the product of modulus. And we can just omit this thing. Because this complex exponential, its modulus will always be 1, and timesing by 1 doesn't do anything. You now just have the modulus of rho equals 2. You can omit the modulus or absolute value sign here as well, because the modulus will always be greater or than or equal to 0. And what does this mean is we need to graph all the complex numbers that has a modulus of 2, which will be a circle of radius 2. It marks a constant distance from the origin. So this is what you will graph. Moreover, you can even generalize this example. If you need to sketch all the complex numbers that satisfy the equation, the modulus of z minus a minus bi is equals to r, where this r is a generic positive number. The result will be a circle in a complex plane, centered at a, b, with a radius r. Why this is true? Because if you let z equals to x plus yi, this ending in a complex number in rectangular form, and you just substitute z into your conditions, the question you are given. So you have the magnitude or modulus of x minus a plus y minus bi. I just basically grouped all the real terms and the imaginary terms here. And you can square it now. Square both sides. You get x minus a squared plus y minus b squared. This equals to r squared. You may recognize it. This is exactly the equation of a circle. Now, you may have some questions. Why do we even want to express a complex number in so many forms? Why can't we just use the good old intuitive a plus bi? What is good for this abstract Euler's form? The answer is simple. Euler's form is very useful when you have multiplication and divisions. When you need to multiply two complex numbers, you can multiply their moduli and add their arguments based on index laws. So this will be very convenient. You have z1 multiplied by z2. So z1 is the rho 1 times e to the power of I theta 1, and same for z2. You can just very easily multiply these two moduli together. And this will be a very easy multiplication, like 2 times 4 maybe, so it's very easy. And for the argument, you just add them up. Example will be pi over 3 plus pi over 6, so it's very easy. You put them up in the exponentials. And for powers, this is a generalization of the Morse theorem. If you have a complex number to the power of n, the same, you express it in Euler's form, and there's a power, you just distribute it in, because you have index laws. And in the end, you have rho to the power of n times e to the power of I n theta. There's also an interesting fact. You can only show it with Euler's form. If you have I to the power of I, and this is like a very abstract thing, you raise an imaginary number to the power of another imaginary number. This is like very weird, but you can actually calculate it. If you remember what I is, it is like a unit vector in the imaginary direction. It has a modulus of 1, and since it lies purely in the imaginary axis, makes an angle of pi over 2 with the real axis. So it will be this form, e to the power of I pi over 2. Its modulus of 1, just you don't need to write 1 there, and the argument is pi over 2. And you raise all of this thing to the power of I. And then you can again use index laws. So basically, why Euler's form is useful? Because you can use index laws all the time. This will be e to the power of I squared times pi over 2. For the definition of I squared is negative 1, right? So you have e to the power of negative pi over 2. In decimal form, this has an approximate value of 0.2079. And this is a real thing, a real number. So it's very bizarre. You find an imaginary number, raised to an imaginary number, and you get a real number out. Lastly, an important note is that if you need to add or subtract two complex numbers, you need to use the rectangular form. So this a plus bi. The reason for this is that when you are in rectangular form, when you add or subtract complex numbers, you basically just add the real parts and the imaginary parts together separately. So this is very to do in rectangular form, but it's not at all obvious in Euler's form. But when you multiply, you don't want to do a bunch of binomial expansions. Like if you multiply two complex numbers together, you have a plus bi times c plus di. That's very, very horrible. You don't want to do that. Just use Euler's form, and it saves you a lot of time. And that's all for today. But beware that there's a lot more to complex numbers than you were taught in high school. You can learn more about it in complex analysis if you choose to do it in university. Anyway, see you next time. Thanks for watching.